Happened. Good. It takes 8 minutes for the light to reach us from the sun. Um, and in my first talk, we actually talked about how far away stars are from each other. I'm just going to briefly go over it. The best thing I came up with when I did all the math on it, if you took our sun, which is about 880,000 miles across, that's really big, by the way. If you shrunk it down to the size of a golf ball, okay, the next golf ball closest to us, if we put that golf ball right here in NorthStar's house, the next golf ball would be just outside of Sacramento. That's how far away that would be. That's why we call it space. There's a lot of space. Just saying. And with that golf ball, the solar system would extend out, twice as far as Yost, give or take. Okay, to the outside Oort cloud, the furthest region from our sun, where things kind of are bound to our sun by gravity, but it's not really going anywhere. It just sends us a bunch of comets that kill dinosaurs and shit. All right. So, but that's one thing. But in our galaxy, something like that, there's hundreds of billions of suns, hundreds of billions of stars. That's way bigger than our solar system. And it already takes forever to get to Pluto. It took us 10 years to get to Pluto with the fastest thing we ever built, which is the New Horizons project. And it was actually fueled by plutonium, which was named after the discovery of Pluto, which is a fun fact on the side. So just given that scale, from here to here, if this was the Milky Way galaxy, which is the galaxy we live in, from one end to the other, it's about 100,000 light years. It takes 100,000 years for light to reach one end to the other. And remember, it takes 8 minutes for light to reach us from the sun. That's a major, major difference. The galaxy is massive, containing so many suns just like our own, and we're finding constantly, every day, planets orbiting stars in our own galaxies. It's fantastic. Moving on to Pluto. I wanted to talk about Pluto. Why Pluto is not a planet. Does anybody believe that Pluto is still a planet? Okay.
Dying on that.
No?
Do we need to get philosophical about it?
You don't have to. We got facts. All right. So, it was back in the late 90s, really, where there are these conventions where people meet together. It's an astronomical convention where people talk about ideas and how we can classify things, and they start talking about Pluto and whether or not we should keep calling Pluto a planet. And they came up with criteria for what you would call a planet. There are 3 things. This guy knows. Yeah? By the way, this is totally informal, so you guys can yell at me. You're totally welcome. It makes me feel more comfortable. Correct me if I'm wrong. I'm totally into that. Whatever. So, but the 3 criteria for a planet. You think about like Earth as a planet. Yeah, we're good. We have a moon, but the moon is not a planet, right? It's the moon. It's completely different. All right. So, what would you call a planet? So, there are 3 criteria for a planet. One is that it has to be kind of big. Okay? Big enough where gravity can actually push hard enough to make it spherical. Most times it's not going to be perfectly spherical, but it's got to make a sphere. Okay? A good example is there are moons everywhere. There are asteroids, there are moons. I think of Phobos, which is the moon of Mars. Actually looks more like a potato, which we're intimately acquainted with, living so close to Idaho, real America. So something has to be big enough to become a sphere for something to be in the running for planethood, if you're going to call it a planet. Okay? It also needs to orbit the sun. The moon is spherical, but it's not a planet. But it orbits us, it doesn't orbit the sun. Okay? So therefore, if something is going to be a planet, it has to orbit the sun. But the last criteria, which, Pluto doesn't really fall into this, and that is that it has to have cleared its orbit. Okay? What does that mean? So, Earth, it has to mostly have cleared its orbit. There's no total thing in this, because we find meteor showers so many times a year. There is still debris left over from the formation of Earth that as we pass through that debris cloud, we get meteor showers. Some of those are left behind by comets and things like that, but some of it's actually left behind by just the formation of our planet. And you see those falling in the sky every night. Actually, fun fact, if you go outside at night and you lay out a big white sheet, you stretch it out in your backyard, leave it overnight, you go through with a really strong magnet, you can pick up iron shavings, it's basically like comet dust. iron that's falling on our planet. 10 million tons a night that our Earth actually gets heavier from just still getting bigger slowly and slowly as we go around the sun. Fun fact, it's totally fun. You should do it. Go on Amazon. Huh? I've done it, yeah, actually. So yeah, we made it, and so we took some iron shapes, we filled it in a little pill bottle, and collected over the course of a few nights.
Will our gravity get stronger?
I mean, technically yes, but not by any measurable difference. Gravity is very, very weak. We can talk about gravity too. When we talk about gravity. It's very, very weak. Okay, so where was I? Pluto cleared its orbit. Yeah. So Pluto just has not cleared its orbit. Pluto is actually not even the biggest thing in its orbit. Pluto occupies an area of space called the Kuiper Belt, which you'd never say Kuiper. If you looked at it, it's like Kuiper, but it's Kuiper. In the Kuiper Belt, there's literally hundreds of thousands of things just like Pluto, mostly smaller, like a kilometer across, or maybe 3 feet across, or maybe even bigger. Like there's something called Eris. Anybody ever heard of Eris? Yeah?
Moon? Mars?
Yes. Absolutely. Sorry?
No. Eros?
Eris. E-R-I-S. Eris. I've heard it both ways, depending on where you're from in the world. So Eris is actually bigger than Pluto. It has a little bit of a different orbit, but it's still basically part of the Kuiper Belt. And it's bigger than Pluto. Pluto has a moon called Charon, which is very similar in size to it. They share a mutual orbit with each other, along with its other 4 moons. Charon, Sharon. Damn it, Karen. Yes. So Pluto, it's just the first thing discovered, and one of the kings, maybe the queen, I would say, of the Kuiper Belt. So it's been demoted to what's called a dwarf planet. But a few years after the whole dwarf planet thing caught on, because there were other things in the asteroid belt, like Ceres, which is actually quite big in the asteroid belt. You can't call that a planet. Pluto's a planet, So, in homage to how we feel about Pluto, they've actually changed it to plutesimals, or plutoids. That's what we're going to start calling these dwarf planets. Yeah, I've heard it called a few different things, but we're naming it after Pluto. And crazy fun fact, the name Pluto actually came from, I can't remember what his name was that discovered it, but he was a really funny guy. When he was asked how he knew where Pluto would be, when he was giving his presentation, there was a big black part of the sky with a couple stars, with an arrow pointing at a black region of space. He says, that's where Pluto is. They said, how'd you know where it was going to be? He's like, well, there was a big arrow pointing at it. It was awesome. A long time ago. But to name it Pluto, he named his daughter, his 8-year-old daughter, I believe, she was 8, named it. Because back in the 30s or so, there was something you would take as an adult called Pluto water. It was a laxative. So he asked his daughter what he should name it, and she said Pluto. So he named it after a laxative. Little known fact. Awesome. So Pluto's not a planet. Here's another one that there was an idea given to me. Have you guys all seen meteor showers? Been outside, seen meteor showers? Yeah. There was actually one just a couple nights ago. It was fantastic, and it was actually really exciting because it wasn't just your standard meteor shower. It happened to be that it coincided with a cloud left behind by Halley's Comet last time I was here back in the 80s. So all of that debris came around, and we passed through basically double the amount of stuff. So it was a really exciting meteor shower, and it was cloudy here, so it sucked. Just saying, we didn't miss much. No, we missed everything, okay. But there's a difference between a meteor, you've heard of a meteorite is different, but there's also something called a meteoroid, okay? This is where astronomy gets really confusing because they're all basically the same thing in different states, all right? A meteor is what you call something when it's falling through space, falling through our atmosphere. You see a meteor falling, okay? A meteoroid is what you call it before it has interacted with our atmosphere. It's outside, it's up there, it's doing something, just not doing anything with us. And a meteorite is what you find and then become rich. They're all the same thing.
It's an asteroid.
An asteroid?
Yeah.
So an asteroid is basically a giant rock, okay? Usually iron rich, silica rich, can have a bunch of other things on it.
Could it become a meteoroid?
Sure, absolutely.
Because it's going to fall in?
Yeah, kind of. So like An asteroid is typically a lot bigger. Like meteors are quite small. An asteroid is basically a much bigger version of that. And this is actually something I wanted to talk about, but I was going to leave it out, but I'm glad you brought it up. But what's the difference between an asteroid and a comet? Good. Yes. So a comet, ooh, what?
What is ice?
Yes, absolutely.
Comets?
Comets are ice. They're a lot of ice. They're kind of this porous rock and ice mixture, which is why when they come close to the sun, they get a tail because the ice starts to boil and evaporate, and it leaves that trail of steam behind it. But what's really fascinating is we've all seen pictures of like Halley's Comet and things like that. So it has this big old tail. Some of them had 2 tails, 3 tails. Cultures all over the world had all these like ideas of what was about to happen when we saw comets with a certain amount of tails. It was ridiculous. Not as smart back then, just saying. But what's really cool is a comet can actually be moving this way, and the tail can be moving that way too. Because the tail is actually not dragging behind the comet. Like if you picked up a tennis ball that's been in a dog's mouth and it's just slobbery, and you throw it, and everything is streaming behind it because of the friction, and all these factors, gravity, things like that. With a comet, the tail is actually caused by the solar wind. The heat, the wind actually being blown from the sun is what's blowing that away. So it can actually be moving that way, but the wind's blowing that way too. There's no atmosphere in space for it to drag into. So it's being blown away by the sun. Really fascinating, cool, counterintuitive idea. Anyway, let's swig it up here. Okay, this one. What are the smallest things in the universe? What are things made out of?
Strings.
Quarks.
I hear strings. Super nerds. Okay. But I hear atoms, which is a very common thing. Who said strings? Yeah? Okay. Let's not get into string theory. Okay, so most people are told that atoms make up everything. And that's clear, they don't tell the truth. But atoms are not fundamental. Which is interesting because atom is actually a Greek word. Atom actually means indivisible. Like there was nothing smaller than an atom. I think it was Democritus who actually came up with the concept for the first time that, if things had to be made out of finite particles of matter or something. Because if they weren't, then how could they move around? They had to be like little balls of something that things could move around. That was how he came up with this, which was way ahead of his time. He was completely wrong, for the right reason. It's fantastic. So he came up with this idea of the atom, and they should celebrate the atom. But atoms are not fundamental. Fundamental particles are actually things that cannot be divided as far as we know now. As far as we know now. That's how you got to qualify it. Because there are things like string theory that actually... we'll talk about that in a second. I'll give a very, very, very brief idea on string theory. So atoms are actually made out of smaller things. So we've all heard of things like protons, neutrons, electrons. Okay, electrons we all use those every day. That's what's making all these lights work. Electrons are on the outside of an atom. An atom has a nucleus. You might have seen pictures. It looks like a little solar system. You have little ball things on the inside, and you have all these things orbiting, whizzing around on the outside. That's what we use to describe an atom. Okay, an atom. The entire periodic table of elements, hydrogen, helium, lithium, boron, carbon, whatever, they all stand for single atoms with a certain amount of protons and neutrons. All right. Starting in the top left, hydrogen has 1 proton, 1 electron. Helium, it's number 2. It's 2 protons, 2 neutrons, 2 electrons. And lithium goes up to 3. These are single atoms. Those describe single atoms. But again, they actually have things inside of them. Protons, neutrons, and electrons. Okay? Protons and neutrons bind in the middle. Electrons orbit on the outside. Protons actually have a positive charge. Electrons have a negative charge. So they kind of hold on to each other, just like a magnet. The positive and negative poles on a magnet actually attract each other. But what's really cool is, somewhere around mid-century, we actually figured out that protons and neutrons are actually made out of even smaller things. which are called quarks. And they actually don't even live alone in there. They're actually, the quarks hold themselves together with another force-carrying particle called a gluon. And then we have electrons, and we have electron neutrinos, and we have muons, and there's this whole family of particles that exist that create the entire universe. And there were things that we couldn't even figure out because they were so small. Everybody heard of neutrinos? Yeah? Neutrinos is this big elusive particle. Back in the early 2000s, there was the missing neutrino problem with stars. The missing neutrino problem, we couldn't figure it out. We eventually figured it out. But the neutrino was so stinking tiny. It was almost so tiny that it wouldn't even be relevant. But what ended up happening, what turned out was, yeah, it is so small, infinitesimal. It's like, why even measure it? It's like gravity. It's so weak. It's so small, why even measure it? Well, it becomes relevant when you're talking about how it makes up the majority of the universe. In 1 square centimeter of your fingertip, 100 million neutrinos are passing through that every second, coming from our sun, that are emitted because of what happens in fusion, which is its own conversation. It'd be fun. We should do that sometime. So it becomes relevant all of a sudden. But I mean, all these small fundamental particles are what caused the universe to be what it is. That's only one aspect of it, because there's a whole other world outside of that I want to get into, which is dark matter and dark energy. The biggest mysteries in the universe, as far as we can tell right now. But before we go into that, I want to just hit before we started about subjects that would be fun to talk about, just briefly. I haven't prepared any of this, so I just figured I'd just rattle off the top of my head. One good one was, do galaxies collide? Okay, these galaxies have hundreds of billions of stars in them, and they're quite distant from each other. The Milky Way galaxy is one that we live in. I did go over this last time, or 2 times ago, but the galaxy we live in has hundreds of billions of stars, and we are indeed on a collision course with the Andromeda galaxy, our closest neighbor, which is about 2.5 million light years away. And we're about 4 billion years from colliding with our closest neighbor. What's really cool is in astronomy, you can actually see galaxies in multiple stages of collision, where they're getting closer, where they're actually in mid-collision, or even in recent days, actually, just recent months, where we're actually measuring the collisions of the black holes in the middle of galaxies, where they whip around each other and combine into one uber galaxy. Ours and Andromeda will actually combine, like I said, in about 4 billion years. And astronomers have come up with a name for the new galaxy, which is going to be called the Milk-Andromeda Galaxy, which is a terrible name. It's an absolutely terrible name. But hopefully...
Could you say that again real loud, please?
The Milk-Andromeda Galaxy. I'm sure they'll... It's just so bad I don't want to say it again. But the cool point about that, galaxies do collide, is that remember when I said that, the whole golf ball thing where we're here and then the next one's Sacramento? So what's so cool is there's so much space between stars that when our galaxy collides with Andromeda, it's very unlikely that any 2 stars will ever interact with each other. What will probably happen is little planets like us might get perturbed and sent out to interstellar space and things like that, but it's unlikely that stars will actually smash into each other. I mean, that barely happens as it is now. I mean, it happens every day, but in the cosmic perspective, it's a very rare occurrence. And there are models, you can look this up on YouTube, of galaxies colliding. It's fantastic to see it. Just big spiraling galaxies that whip in and become one massive galaxy. And I think there actually is a visualizer that actually simulates the Milky Way and Andromeda. So, and again, on this is my first talk here, we talked about the local group of galaxies. We live in what's called the local group, where we are combining with other galaxies around us. There's 54 galaxies in our local group. The 3 largest are the Milky Way, Andromeda, and the Triangulum galaxy, and the rest are all dwarf galaxies. They're very small, like the Large Magellan Cloud if you're down in Australia. That's a dwarf galaxy that's attached to us. So that's really fantastic. But we're all on collision courses with each other. We're going to make one big uber galaxy. Andromeda. Triangulum. Plus 53. Okay.
I'll apply some drama to your Dromeda.
Yeah, it's just going to sound like a big drunken thing. which is easy for me, clearly. Okay. I could go on to more. That's actually, I should have done that one last because that segues into another point. But this is another cool point, which is we think of things as hot as being red and cold being blue. Okay? Now, stars are actually classified by their temperature. Okay? There's like they're classified by letters. So O, E, A, F, G, K, M are the types of temperatures we observe. The coldest stars are actually red, and the hottest stars are actually blue. It's a little counterintuitive. Blue stars are typically a little bit smaller. Red stars are really, really big. And that's not always the case, depending on the stage of the star's fusion process. But stars that are really, really hot tend to be really, really blue. You can actually do that here. If you take a acetylene torch and you light something on fire, which is really fun. We should do that like later. Let's have like 11 beers and light stuff on fire. Yeah, on Thursday. Because can. Okay. Old saying. So if you heat something up, you'll slowly start to see it turn red, right? Stars do this. And you'll start to slowly turn it red. And if you can get hotter and hotter and hotter, it'll start turning like yellow. And then eventually white. At the high end. But it'll actually go through all these stages of like blue. It'll actually get blue hot when something's really, really hot. Think about like a candle flame. The hottest part of the candle is actually blue. And then the coolest part is like an orange. This one on the top. Where it's closest to the point of ignition, it is the hottest, and that is a blue flame. Stars are the same way. The hotter stars are blue. All right. I think this one's yours. Will the sun kill us? Short answer, probably. It could be for any number of reasons. And again, I'm combining ideas here, but stars are doing things. They're not just kind of sitting there giving us free heat and energy as we see it every day now. They kind of go crazy sometimes. They set off these massive solar flares. We've all heard about solar flares. Some can be so energetic that it can kill everything all at once. And you wouldn't even know it. It just all dies. So back in 2004, 2003, we discovered Kepler 452b. All right, Kepler named after the telescope, which was named after the guy Kepler, Johannes Kepler. So that telescope, its entire mission is to look for planets around other stars. Okay, Kepler 452b is a planet orbiting another star that's just like Earth. It's actually still to this day the most Earth-like planet we found. Last year, we were looking at it, we're like, man, it's got oxygen, it's in the right distance from its host star to have liquid water, and have life on it, let's go there, because it's actually kind of close. And it got hit with a massive solar flare so powerful from its host star that it would have killed everything on its surface if it existed the same way that we did here. Even extremophiles. Like tardigrades and stuff, all dead. That's what stars do. Our sun might do that someday. I'm sure it's happened before, and we're sure it's happened before. So that's the first thing. Also, as the sun begins to age, it's going to actually expand. And I went over this in my last talk about how stars die. But as the star begins to consume all of its fuel, it actually gets bigger. The outside parts get bigger. Okay? Reference my last talk. If you want to talk about it, we can talk about it afterward. But it actually starts to expand outwards. And as it does that, it's going to actually engulf Mercury and probably Venus. And depending on the model you look at, whoever you trust, it could also completely envelop Earth. I would say from what I know, which is limited, but from what I know and talking to whoever I talk to, Earth will probably not be completely enveloped by the sun, but it will probably vaporize the surface. So those are two very different things. Just because life isn't here doesn't mean Earth dies. It just means we die. But we probably won't last too long anyway because, there's that, and we might just nuke each other. So we're going to get into that a little bit later. All right? But, okay, we're going to skip the last one. We're doing good on time here. I want to talk about, briefly, the biggest mysteries among astronomers and cosmologists. So some misconceptions. Let's hit massive mysteries, and they're both dark. Have you guys heard of dark matter? Yeah? Anybody not? Then you can raise your hand very, very slightly. Don't lie. I know you have. Alright. How about dark energy? Have you heard of dark energy? Yeah? No? Okay. It's okay. So, those are two very, very different things. Okay? So, you hear dark matter and dark energy thrown out there as if they're synonymous or if they're related to each other. And there was a concept that did tie the two of those things together a few years ago. It was called dark fluid. If you go online, you won't find anything about it because it's clearly not right. Actually, one of the coolest things I've ever done was actually I had a debate with the director at the Canada-France telescope in Hawaii about dark fluid. He was a big proponent of dark fluid, and I mean, that's yesterday, but it was really fun. So dark fluid is not a thing. If anybody ever says it is, just tell them they're wrong, and you'll be fine. You're right. So dark matter and dark energy are two different things. So let's talk about dark matter. So we're made out of stuff. You and I, planet, concrete, galaxies, stars, dust, hydrogen clouds, everything is made out of stuff. Let's just call it stuff. Those are atoms, okay? Remember when I said atoms don't make up everything? We're gonna hit that really fast. So all the stuff, think about how big the universe is. It's massive. It's 13.8 billion years old. We look in any direction, we see that far into the past. Doesn't mean that that's how far things exist. It's actually 96 billion light years across, with recent surveys showing 2 trillion galaxies in the visible universe. Not just the observable, but the visible universe. All of that stuff, galaxies, everything, all the things we see are made out of atoms. Atoms make up 5% of the universe. The rest of it is made up of dark matter and dark energy. We have no fucking clue what it is. Spoiler alert. Okay? Great ideas. The ideas are quite complicated, but so we being 5% of the universe, us, stars, everything, 27% of the universe is made up of this thing called dark matter. Okay? So back in the, I think it was the 30s, there was this crazy Swede. His name was Fritz Zwicky. It's crazy. Everybody hated him and loved him at the same time. He's just one of those eccentric guys that just said everything that was on his mind. I know a guy just like that. And he was obnoxious and had all these crazy ideas. He would throw out things that were so crazy that everybody just said, okay, it's just Zwicky again. But he actually came up with this idea a long time ago. And what he actually did was he started looking at basically, he was looking at what's called the bullet cluster of galaxies, so a big cluster of galaxies, and he was looking at how fast they were spinning. Okay, him and this woman astronomer, Vera Rubin, actually back in the 70s, she spent 10 years looking at this. Now let's just think. So we're gonna do like quick physics. This is gonna be easy physics. You can do it. You're fine. Yeah, good. So. Think about something, like the harder you pull on something or push on something, the faster it moves, right? Okay? Galaxies are actually, when you look at a galaxy like this, there's all kinds of stars, and they're actually in orbit around a supermassive black hole, or a massive region of gravity in the middle of the galaxy. Now, just like our solar system, Mercury moves really fast. Venus moves slower. Earth moves slower. Mars moves a little bit slower, because they're not under as much of an influence of gravity as the closer planets are. Okay, the harder you pull on something, the faster it moves. Now when he, and then later Vera Rubin, were observing the stars on the outside of a galaxy compared to the inside, they're moving at the same rate. Super weird. Doesn't make any sense. What the hell could it be? That's what he said in Swedish. Whatever. Okay. So they found out that there was 400 times more matter in galaxies than what they measured by looking at how many stars were in them. Okay, then they siphoned out all the other, like, what could it be? Could it be black holes? Could it be brown dwarfs, things that we can't see with visible light? You know, could it be just like all this missing mass? No, they added it all up. They looked at how often we see things like that in our own galaxy compared to other galaxies. You can actually detect things like that by other means. So we filtered out all this data and we found out that there's all this missing matter. And we call that dark matter. There's this stuff that exists that doesn't interact with light. We can't see it, but it's there and it makes up more of the universe than what ordinary matter makes up. It's fantastic. It's totally crazy. I can go crazy on dark matter. It's super, super, super cool. But I'll give you the gist of it, what makes it so hard to detect. Okay? You and I interact with light. You know how we can tell? We can see each other. Okay? When photons, when they interact with you, they slam into atoms of your body, they make electrons jump out, and then they don't want to be up there anymore, so they go back down, they emit another photon, and that gets flying towards each of our eyes, and we see each other. Like, we interact with light. We interrupt light. It's the photons, the light themselves, they get absorbed by the atoms in our body, and they emit something, and color comes from that. It's a fantastic idea. It's great. Dark matter doesn't do that. Light passes straight through it like it's not even there. It's crazy, okay? But it gets crazier. It doesn't even interact with itself, and it doesn't interact with ordinary matter in any way other than gravity. Okay, let me explain that. So you and I can touch this and it stops me from doing anything. Okay? We're made out of atoms. The electrons that are on the outside of my fist are interacting with the electrons that are on the outside of the whatever this is made out of, and it keeps me from going through it. Okay? That's a common thing that matter does. Rocks, everything, planets, galaxies, they do that. Dark matter, it sees itself and it just passes straight through itself. No interaction whatsoever. If it reaches ordinary matter, it goes completely through. It doesn't interact at all. Photon sees it, it doesn't see it at all. It doesn't interact, it doesn't scatter, it doesn't do anything. It's completely dark. Okay? But here's the cool thing to think about. This is a very chicken or the egg thing that I was talking to you about earlier. I was talking to another guy too about galaxy formation. So.
We talk about that a lot, dude.
Oh yeah. Especially on Thursdays. What days is it? Okay. So think about that for a second. When ordinary matter interacts with itself, it tends to it interacts. It bounces, it recoils, it loses energy, it takes a minute for it to do its thing. Dark matter, it passes directly through itself. That very fact, and the fact that there's so much of it, and it permeates the entire cosmos, means that it can collapse on itself sooner than ordinary matter can collapse on itself. It does less shit. It doesn't do stuff. It collapses into itself sooner via gravity. Because that happens, yes?
You sound like you're describing empty space to me.
No.
It sounds like empty space.
It's not. It's stuff.
But you just said it doesn't interact with itself, it doesn't interact with light, nothing interacts with it, like,
Okay.
what to say it is something.
No. Okay. Good question. Because
So, am I the only one feeling this part? I don't know.
no, I'm glad you asked it. Because if anybody else thinks that same thing, well, let's clarify.
I'm just at.
It doesn't interact with itself, but it interacts via gravity.
Okay, so when the planets are traveling around the outside of it, they're traveling the same rate because gravity interacts.
Yes.
Okay.
So when I'm talking about when it actually collapses, it observes the same law, which is called the law of angular momentum in physics. So things don't always just fall directly towards each other. They kind of get in these near-miss accidents. But because they're still kind of like holding on to each other via gravity, they'll pass by each other, but then they'll pass by again. And as they do that, they're going to slowly wind down.
Spirograph. Have you ever seen
Yeah.
one of those?
Absolutely, spirograph. So, does that make sense? If something winds down because they're bound to each other, they observe that law of angular momentum. They're mutually bound to each other via gravity. The thing is that they don't lose energy and get slowed down by interacting with each other, like ordinary things would. Okay, so if things like us, ordinary matter, were to follow that same procedure, if they did come close to each other, they would hit each other. There'd be a recoil energy. It would slow things down. It makes the actual process of collapsing much, much slower. But
Dark matter does that?
But dark matter can do it faster because there's no time wasted by interacting. It collapses sooner because it's not wasting time interacting with something else, other than gravity itself. Does that make sense? So, when this happens,
Not really, but yeah.
yeah, it's fantastic. So because it does that, but it still observes that same law of angular momentum, things tend to spiral, and it creates the foundation of gravity, a place for things like ordinary matter, which again doesn't interact with dark matter other than gravity. It has something to fall into. And when that happens, you have the beginning of what a galaxy is supposed to be, what we observe as galaxies. And because there's a big, it's called an accretion disk, it's a flat disk of dark matter. This flat disk of dark matter in our galaxy, in all galaxies, are what all the stars, mass, and everything wants to be around, and it follows that same track. And there's so much dark matter compared to ordinary matter that it overwhelms the density of matter from ordinary stuff in the middle. The dark matter is so abundant, and it's so evenly spread out, that on the outside, the stars that are falling into gravity, and the gravity is making them move, they move at the same speed as they do on the inside of the galaxy. They don't operate the same way as the solar system. They have their own set of rules they abide by just because dark matter is there. That's actually how we know it exists. That's how we know it exists.
We can measure its size and stuff. We can see that.
We
measure
can
it.
see what it's doing, but we have no fucking clue what it is. We have no idea to know what it is, what it's made out of. There's no way we can do it because it doesn't interact with light, which is how all of our instruments to detect things work. We're made out of stuff, and if it doesn't interact with stuff, then how do we use stuff to figure out what it is? We can't do it. It's super hard. There are some ideas. There are some ways we're coming up with. Okay. One is called the WIMP model. One is called the macho model. Which is really, really funny that it ended up that way. They're both acronyms. The WIMP is probably the most likely case. It stands for weakly interacting massive particle. It would be probably 20 times more massive than the Higgs boson, which already took us this long to find. So we need to build a particle accelerator that's not 20-something kilometers around, but more like 200 kilometers. And we should have built it in Texas, but Clinton was an asshole. Okay. Thank you, Congress. All right, we would have figured that out a long time ago. But I could go on clearly. I'm very passionate about dark matter. But let's quickly hit dark energy, which is very, very different. Dark energy, okay? Think back to 1929. Who was around back then? Yeah? Yeah, see? All right. Reincarnated. Yeah, all right. So back in 1929, there was this guy. He was kind of an asshole, but still, I like what he did. He quit his job as a lawyer, making a lot of money, to become a full-time astronomer. His name was Edwin Hubble. And he was up on Mount Wilson, just outside of Pasadena, California, with the largest telescope at the time, which he privately funded partially. And he set out. He actually discovered that galaxies actually exist. That there are island universes outside of our own. He discovered the Andromeda Galaxy, which I talked about briefly last time, by seeing a particular type of star in that galaxy. But when he started observing, when he figured out that galaxies exist, and we're not the only one, he started looking at galaxies everywhere. They were called spiral nebula at the time. Nebula being cloud, because when you look at galaxies in the sky, they look like little fuzzy white things. They look like clouds. So he started measuring these particular types of stars, supernova, and what's called a Cepheid variable star, which are always the same. And he started measuring the spectra from these stars. Okay. He started measuring the rate of the galaxies actually moving around. So there's this thing in astronomy called redshift and blue shift. Okay, it sounds complicated. It's very similar to not Rayleigh scattering, but the
Rainbows.
Doppler effect. Yeah. So if you hear like an ambulance go by, you can hear as it drives further away, the sound frequency drops. Okay, because the sound wave lengthens. Because the space that's between us and it is becoming bigger. So it's emitting the same frequency, even though the space is getting bigger, because there's a bigger area for that sound to be in, it drops in frequency, it becomes a lower sound. Okay? Light does the same thing. Okay? Now back in the late late 1600s, Isaac Newton first passed light through a prism and found that light can be scattered out into all of its fundamental components. Science majors in here? Good? Yeah? You are? Good? So every atom in the universe has a unique signature, a fingerprint. And when you look at a rainbow cast by a prism, light passing through a prism, every atom actually has these black lines going through them. They're called spectral lines. And everything has a unique fingerprint. Now, it's the same everywhere in the universe. You can almost think about it as the shadow being cast from the cloud of electrons in a weird way. But every atom is the same in the universe. Now, what's really interesting is if you look at other things, if they're moving away from us, those black lines in this rainbow, they actually move to one side or move to the other. But if everything's the same, but these lines are in different places, what could that mean? And what that actually means is that something is moving away or moving closer to us. When something is moving closer to us, we call it blue shifted. It moves closer to the blue end of the spectrum. It becomes higher energy. If it's moving away from us, it moves to the red end of the spectrum. It becomes lower energy. Okay? And if we have the same atoms, the same signature we measure from everything, and then we know exactly what it should be, exactly the picture it should be, and then we see something and it's different, we can measure the difference between where it is and where it should be, and then infer how fast something is moving away from us or moving towards us. Edwin Hubble was able to do this back in the 20s, and he actually found out that the entire universe is moving apart. Okay? Yeah.
Is this how they also found out, like, that there's, like, because I was kind of curious about this, but light's coming at us, how do we know how old that light is, kind of, you know, like, you have we measure the universe as 14.8 billion years because of the distance that light we've detected, we say, and that's kind of, is that how that is measured out then?
Does it have to do with the source?
Yes. Yeah. So the source of light is the answer to that question. So you think about it that if you have a 100-watt light bulb, and you know that light bulb is 100 watts, if say you put it over there, and I put a detector here and say how many watts am I receiving, okay, you can actually, if you already know what the wattage is of that, and you know how much you're receiving, you can actually calculate the distance you are from that light bulb, okay? You can do the same thing with stars, because there are certain stars, like I said, there's what's called a Cepheid variable star, which a Cepheid variable is a star that actually gets more luminous and less luminous over a certain period, and the periodicity of that would correlate with the mass of its star. There's another thing you can do, which is a type 1A supernova, which is a very specific type of star explosion, that when it explodes, every single one in the entire universe explodes with the same luminosity. It's called a standard candle. So we know that's a 100-watt light bulb. So all we need to do is measure what we see when that supernova goes off, and they're super bright. I mean, when supernovas go off, because you think, like, we can't see galaxies in the sky, like, how can you see a freaking supernova 13.8 billion light years away? The answer is that a supernova, it puts out more energy in 1 year than every star in the entire galaxy that is within. It's literally 100 times brighter than the entire galaxy when it blows up. So we can see it from really far away. That's how we know how big the universe is. All we need to do is look at those types of supernova and then figure out how bright it is with really powerful telescopes, mind you. So we should fund those and pull them over, especially the 30 meter one in Hawaii.
So that gives us kind of like a general idea of how old that section might be.
Yeah.
Okay.
Yeah, totally. We can actually get all the way to the edge of the universe now. Of how far.
A supernova out there. We know the wattage of that supernova, and that's that far away.
Yeah, it's always the same. So my last talk, I talked briefly about it, but there's a function that happens. It's caused by two stars that are interacting with each other. One's actually siphoning off fuel from the other's sun, and when they reach a very specific point that's when it detonates, is when it reaches a very specific point, and they're all the same. They all attain the exact same mass. Because they have the exact same mass, they have the same amount of energy, because energy and mass are equivalent, E equals mc squared. So because we have that, we know exactly how bright it's going every single time. And I mean exact. I mean, these guys won a Nobel Prize for figuring this out. Indian guys. It's called the Chandrasekhar limit, or degeneracy pressure. So that's how we know. If that makes sense. So, but here we go. So I'm gonna have to run through this really fast because we're running out of time. But so we figured out that the universe was actually expanding away from itself. Now, the universe is expanding, yes. We knew that the universe had this big bang and exploded outward. So back in the 90s, a team of scientists went out there to actually measure the rate of deceleration. How fast was the universe slowing down? Okay? This actually happened in Hawaii. In 1999, I wrote the guys' names down because I want to give them some credit. Saul Parmiter, Brian Schmidt, who I've actually met, and Adrian Rice. They figured this out. So them and another independent team in another part of the world, they set out measuring the deceleration of the universe. How fast was the universe slowing down in this expansion? Which makes sense. It would make sense because if gravity exists, which we all kind of, we know it does, if everything's kind of bound to each other and it's blowing away, gravity should grab onto it and say, okay, slow down, slow down, slow down. And the original idea was that the universe was actually going to collapse back in onto itself. It was called the Big Crunch. This was the idea. So this team set out to measure the rate of deceleration, and they measured that the universe is expanding and accelerating. It was like the biggest non-result. They just came back and said, that is completely the opposite of what we were looking for. They all won Nobel Prizes. They proved that the universe is not only expanding, but accelerating in its expansion. And there's this energy that makes up most of empty space. We call it dark energy, and we have no fucking clue what it is. When I said we make up 5% of matter in the universe, that we make up 5% of the universe, dark matter makes up 27%, dark energy makes up 68% of the universe. It's been staring at us the whole time. We had no clue how to detect it. It is most of the universe. It's crazy. It doesn't dilute. As the universe expands and gets bigger, it gets stronger. It's fascinating. It's so strong that there's what's called the Hubble constant. It's something that Hubble measured, which is the further something is away from us, the faster it's actually accelerating away from us. Okay? So if something is 3 times as far away, the Hubble constant is if something is 3 times as far away, it's moving 3 times the speed. If it's 4 times as far away, if you give it a distance, it's moving 4 times the speed, so on and so forth. So the further you go away, the faster something is receding away from us. That is the expansion of space itself. Has everybody heard that the speed of light is the fastest thing in the universe? Yeah, that's true. That's the fastest anything can move through space. But there comes a point on the edge of the universe where space itself is expanding faster than the speed of light. Okay? And because of that fact, there comes a point where we actually can't see anything because the universe is expanding faster than light can propagate through it. So there is a limit to what we can see. We don't know how big the universe is because of the way that it's expanding. It's fascinating. This dark energy, we have no clue what it is. Einstein actually referred to this part of this as his biggest blunder. He actually built in this thing called the cosmological constant. I'm not going to go into it. That's going to get a little too complicated, so I'm just going to skip it. So let's talk about aliens. The universe is expanding. We're good. So who thinks that there's aliens out there?
I do.
Yeah? Cool. Because math?
Behind the math, there's no way that we're probability. There's no way.
Cool. Well, I'm going to use some accurate math to disprove you. Cool. So we should qualify that, though. We should definitely qualify that. What is the odds of life existing in the universe? Probably really, really high. What about intelligent life? What is life?
What is life?
So it depends who you talk to, but from everybody I've talked to, life, I've gotten into philosophical conversations about this before, it's fantastic. So life is something that experiences like a anaerobic digestion, or something that consumes something, gains energy, and then releases waste, and something that reproduces. Those are the two criteria for life. From most people that I talk to, biologists, a lot of them in Hawaii, especially marine biologists, but I mean, they're just marine biologists, they don't count. I mean, using that same definition, you can say an idea. An idea is life. It's something that consumes it, like a good idea makes a bad idea die. It consumes it, it might keep the good stuff. I mean, think about Christmas. Christmas is just Saturnalia without the orgies. I mean, I would argue that we got rid of the good stuff and kept the bad stuff. So maybe that idea is not it's not evolving properly. Okay. So, anyways, that's how a biologist would describe life. But that's a good point. Is life based on DNA? You know, like we have a sample size of 1, which is us. You know, a sample size of 1. We have the 4 things that make up our DNA, and that's it. Could it be something else? I think you were asking, what, could there be other types of life out there that's not carbon-based? This mic stand is doing its...
It's not a fan.
It's not. All right, let's do Steve Tyler. Okay, here we go.
Obviously, it's getting outsourced.
Right. So I don't know a lot about this, but I'll tell you what I do know, and that is that most people would say that if something were not carbon-based life, the logical thing it could be would be silicon-based life. You heard that before?
No.
So if you look at the periodic table, you see carbon, which is what row is that in? I can't remember. But if you go directly below it, the next thing down would be silica. So it would actually bond with like valence electrons around it. So, and again, I don't know a lot about this, but from what I've heard from people that know a lot about it, is that you don't need to do that because there's so much more carbon in the universe than there is silica. And it takes so much less energy, which the universe is super lazy. It does not want to put energy into anything. You know, it's like a teenager. I mean, it is kind of young. Okay, it doesn't want to put any energy into anything, so it's going to take the easiest possible route. I mean, honestly, that's a foundation of thermodynamics, you know? So if the universe operates a certain way, it's going to take the easiest possible path. I'm going to give you a real crazy spoiler alert. So one of my favorite cosmologists, he was on an airplane going to a conference, and he was writing a paper, and this guy next to him, he's like, oh, yeah, I know all about that. He's like, oh. He's a very famous cosmologist, so he's like, he hears theories from people all the time on airplanes, I'm sure. So he's like, oh, really? He's like, oh, yeah, I completely understand the purpose of life. He says, okay, it's going to be a long flight. I'm telling you a story. And the guy says, yes, I believe that the purpose of life is to hydrogenate carbon dioxide.
It's to oxidize.
What does that mean? To hydrogenate carbon dioxide. So carbon dioxide wants to be methane, okay? But the only way for carbon dioxide to become methane without violating any laws of thermodynamics and entropy and whatnot is by way of anaerobic digestion. The only way for the universe to become what it wants to be without violating its own laws is to create life itself. This is a really, really clever way of saying the entire purpose of life is to fart. Yes. All right. So every time you fart and somebody gives you a hard time, say you are fulfilling your destiny. All right. I gave you something to give for the day. So what were we talking about with life? Life. I just want to start farting. Okay. So what are the odds of life existing outside? So simple life is probably very, very likely. I mean, there's a lot of stars, a lot of planets out there. It's crazy out there. But like, maybe let's talk about intelligent life. You know, the universe, it's old, but it's not that old. Okay, it's 13.8 billion years old. But from what we can tell, the last star will die out in 100 trillion years? Okay? Do you remember my first talk? I said the difference between a billion and a trillion? Okay? Just quickly, a million, if you counted to a million for every second of your life, it would take you like 11 days. If you counted to a billion, it would take you 33 years. If you counted to a trillion, it takes 33,000 years. That's a big difference. Okay, that's a huge difference. Now the universe is going to be really, really old. And it's really young compared to when it started. Our sun, for example, is only a 4th generation star. Suns are old, stars are old, they die, but we're only on the 3rd and 4th generation stars in the universe. They haven't gone through these cycles to create heavier and heavier elements. They start simple and just basically fuse up to carbon. That's it. No uranium and iron and silica, there's none of that. It just stops at carbon and it dies. It has to create, planetary nebula and then come into a proximity of another gas cloud and create another generation star to create something even heavier and heavier. It has to die a few times. It sounds like a common story. Something has to die a few times for things to actually exist, like us.
Oh no.
Yeah, okay. Sorry, I'm going on a rant there. So our galaxy is about 8 billion years old. And we are, again, in the 4th generation star here, which the stars before us died so that we can be here because they made heavy elements like the iron in our blood, the calcium in our bones, the hydrogen, the oxygen, it's what makes up our water. Those stars died making the elements that make us what we made out of star stuff. That's the second thing, like so cute.
Yay.
So,
What was that one more time?
London. What's his name? Andrean. God, they have the most amazing love story. He proposed to her over the phone. Adorable. Okay. So, anyway, so let's talk about some. I'm just gonna skip ahead here. We're gonna talk about what's called the Fermi paradox. Has anybody heard of the Fermi paradox? Yes. We'll talk about the Drake equation. Okay, so there's this guy named Enrico Fermi. He's one of the founding fathers of quantum mechanics. So he was actually sitting, working on the Manhattan Project in Los Alamos, developing the first atomic bomb that helped win World War II. And he was sitting with a couple of his colleagues, and they were talking about aliens. This quiet moment came upon them. And he was a notoriously quiet guy, really smart, but very quiet. And he was sitting at lunch, and he just screamed out, "Where is everybody?" It's like quieted the whole cafeteria. At least this is the way the story's been told. I've heard it. They're like, "What do you mean?" He's like, "Come on, we're physicists. We know how to calculate this shit. We know the probability of life existing. So where is everybody? It seems so likely, even with the most improbable case, which is what we think we are. It's so improbable that life exists. It's so improbable that all these things come together to make life, but that number is still, it happens every day and somewhere in the galaxy. So where is everybody? Why don't we see them?" And this whole discussion started happening. They came up with this idea called the Great Filter, which makes a lot of sense. And it makes a lot of sense thinking that they were working on the Manhattan Project. Those guys knew what they were doing when they went to work on it. They knew they were building something that its potential was, it could vaporize it could completely destroy our atmosphere and kill us instantly. Like, they actually took bets